All right, let's have some important announcement quickly, and then we'll get to the materials. Your lab number 2 will be due this Friday. I'll release the solution right afterwards. And then you got your programming test number 1 next Wednesday, right? If you look at the calendar, we're just sticking to it. I just released 2 things, which I would like to draw to your attention. All right, so if you go to the E-class, under the programming test section, you got the practice test number 1. You can definitely try it out as if it's a test. You can set yourself a timer like a real test and give a try. And then I'm going to give you the solution for the practice test maybe a little bit later so you can try it out yourself. That's really important. So I'm going to release the solution to practice test 1 either later Friday or over the weekend around that time. But you should really try it out first. And there is also an important document you want to really go through, pretty short. I'll highlight something to you. If you go to the lecture site and make sure you refresh your browser, there is the guide for the programming test number 1 there. Right? Let's take a quick look. Some parts. Right? So it's going to be next Wednesday, October 9th. It will be during your enroll section there. And that you know the venue of some building. You will be given 50 minutes. And then it's back to back. So, yep, that's kind of the hardest I can push for now. And then make sure you go to the right section there. And then there will be some rules that you want to follow. And about the structure of the test. Basically, it will be very similar to lab number 2. You will be given some informal description about the problem. You will have to formulate them into rodent machine. And make sure you know how to create a project from scratch in rodent. That's something we taught you in lab 0. Right? So when you guys see the the practice test 1, that should prepare you quite well about the format for the test. Right? So make sure you do them. But the level of difficulty in the actual test could be higher, but the format will be the same. Okay? Let me tell you right at the front. All right, so, in terms of the text, because some of you were concerned about it, so this will be your answer. You don't necessarily have to memorize all the ASCII syntax for the different relational set or functional operators. So I would say this will be the document I'm going to make available to you. Most likely, I'll put it on the desktop or maybe the home directory when you log in to the machine during the test. So get yourself familiar with this document, which I already referenced you to earlier. So that one contains mathematical definition, ASCII syntax for the different operators that you may want to use. Make yourself familiar with it. But I would say for the common ones, you may just have known them pretty much by heart already, so you don't really have to refer to them. But the document will be there, just to let you know. That's the only thing. And all your notes, all your slides, and any other website, they will be blocked during the test. And the coverage will be lab number 1, lab number 2, right? So lab number 1 is important. I will try to go over the remaining part of the solution of lab number 1 today after we cover more functions and relations. We'll talk about it maybe towards the end. And I will also try to maybe look at the beginning part of lab number 2, especially axiom number 3, 4, and 5. I heard from the TA, maybe you're still struggling a bit about how to understand them. So I will help you. But for the actual task number 2, for your lab number 2, you have to still do it and then maybe drop out a scheduled lab session tomorrow to get some help. But for today, I'll try to help you a bit, understanding the requirements, the invariants. That might be what you're struggling the most. And it will be also very helpful if you also study the math review lecture for the test. All right? All right, practice question, as I said, is already on the E-class. Feel free. And this is just some instruction for helping you to simulate the test. I would say set yourself a timer. 45 minutes, 50 minutes, up to you. Okay? And you can also even practice submitting. I also put a link over here. All right? All right, that's about the programming test 1. Do you guys have any question, any concern? Okay, we'll see. Okay, after next Wednesday. Okay. And I'm thinking that maybe we can confirm on Thursday. Potentially, we can run maybe a review Q&A session over Zoom if you guys want to ask me some questions about the concept, right, for programming test. It can be either Friday or maybe Monday, right? So could be maybe PM, when you guys are more free. I'll think about it, but if you guys have any preference, feel free to mention that to me after the class, and then I can decide on Thursday class, right? Think about it. If you find it useful, I'm happy to spend some time to help you. All right, so let's now move on to our materials. So what did we talk about last time? Let's now do a very quick recap, and then we'll continue with overriding. All right, so last time we spoke about more operators. But in the beginning, we talked about something very important. We talked about this symbol here to say, given two sets, S and T, the order matters. And we say, well, it'll be the set of all possible relations that can be constructed out of these two sets. And whenever you want to declare a single relation, you will use this membership symbol, right? And then we say that this notation here is just equivalent to the power set of the cross product, right? Make sure you really understand these important points. Make sure, right? Of course, in the actual programming test, if you declare one or the other, if you got error from one, you can try the other. That's okay. You might just get them to work. But in the actual written test or in the exam, you have to make sure you put the right thing, right? Anyway, study that and let me know if you got trouble understanding. I still got office hour on Thursday. And we spoke about some optional exercise. And then we talk about domain, range, and inverse, and some algebraic properties, right? They are straightforward. We'll see more today in the beginning. And we'll talk about image, which is also not too bad. And also we'll talk about some further algebraic properties to understand different operators working together. And we talk about the domain and range, either restriction or subtraction. Right? So just remember the symbols on the paper and also the symbols you have to write in Rodin. You may be asked to actually write something like that in the actual test. But as I said, I'm going to provide a PDF summary to you, so you may want to look ahead to see where you can find the symbols. So in case you need some reminder, go to the PDF. All right, so these are the examples we did about the 4 operators. And we got relational overriding. That's where we stopped from last time. So before we continue from here, do you guys have any questions about what we spoke about last time? Any question? Everybody's good? All right, let's now move on. Relational operators, overriding. And I will talk slightly a little bit more about relational operators, and then I can move on to talking slightly about lab number 2, just to help you. For those of you who might be still struggling with task number 1, understanding celebrity 0. Overriding. This will be the symbol. And just remember, for overriding, it's a binary operator. We got relation and relation. You would say a relation R is overridden by relation T. So you would say something like the relation R is overridden by another relation T. And the result from this binary operation is just another relation. Okay? How do we see that's a relation? You can see from this set comprehension expression here, to the left of the vertical bar is a pair, order pair. So the result is going to be a set of order pair. So it's a relation. And we say that there are 2 parts over here. This will be part number 1. This will be part number 2. And you can see there is a disjunction over here, right? You don't need to prove it, but there will be a nice property over here. So when you have a set comprehension expression, let's say I got some x and y, order pair, such that I got one property P1, xy. Or I got another property P2. And it will be a nice compositional property I can consider. I can somehow turn this guy here into a union of the 2 condition set. All right? That will be also helping us understanding the relational the overriding. So this will be basically xy. And one will be just satisfying P1 xy. And we're going to put a union over here, which corresponds to the disjunction over here. And also we got xy such that P2 xy. That's a nice property. This one here, and of course you got union. All right, so we can use that right away. So now let's rewrite the overriding expression. So that one there by definition will be equal to two sets. So the first set, dr prime, and then dr prime t. All right, that's the first one, right? To the left of the disjunction. And let's now turn this disjunction over here into union. And then we got another set. Also dr prime such that, right, I'm going to copy this condition over here, verbatim. Dr prime in R, and D is not in the domain of T. All right, we got two sets over here. Set number one over here, set number two over here. Right? Hopefully so far you're still comfortable, right? Manipulating the symbol a little bit. That's going to help. Well, to be honest with you, don't you think this one looks something pretty straightforward? What's this? What's this set? What's this relation? We're saying, give me all the pairs where each pair is in relation T. What do I get? T, right? The same relation. So it's going to be just T itself. All right? And then we're basically saying this one here. Let's now take a look at this one slightly more carefully, right? What are we saying here? We are basically saying, give me all the order pairs. Each pair is in relation R. So it's basically like an R, except we're going to somehow not including those not in the domain of T. Doesn't that sound like something we talked about last time? Okay, I heard some keyword over here. I heard restriction there. Okay, it's on the right track. Guys, let me say it again. We're saying that all the pair that's in R, but those pair should not be in the domain of T. Should not be. Is this more like a restriction or subtraction idea? Somehow we want to exclude those that are actually in T, right? We want to keep those that's not in the domain of T, right? So now, how do we rewrite this expression over here? That's some question for you. That's actually one of the problems I'm going to solve in the actual slides. But let's now rewrite this. What's going to be like would be this part over here is the idea about R. And this part over here is a little bit about some subtraction. We want to exclude some pairs from R. What exactly are we excluding? We're excluding those whose first element is in the domain of T, because they should not be there. All right, so finally, this is what we will have. Union. And then we're going to get some domain subtraction. So that will be R, like here, subtracting everything that's in the domain of T. So the domain of T. And domain restriction will go like this, right? But now it's subtraction, so we should go like that. This is the answer to one of the problems which I put on the slide. But let's solve it together. That's okay. So the way to understand relational overriding over here, the way to understand it would be, of course, you got to understand the formal definition, number one. And then somehow we can do some nice rewriting into union, and each individually being considered, it will be easier to see. It's like a union of the T, the second operand over here, and also the first operand here, but domain subtracted by the domain of T. Right? That's something you want to keep in mind. Might take some time to get used to, but that's the derivation process. All right, so now let's now do one example about overriding. And of course, once we revisit your lab number 1 solution, one of your lab 1 events will actually use the domain overriding. And that's also one of the most common questions I got from you guys. But that's something we can revisit again, just to reinforce the idea. So let's now take a look at this example here. Okay. Let's now do this one here. I'll make some space. Oops. Let's now do this. There we go. So what we want to do is we want to do R overridden with the T. And now let's put the T, which is in a set of order pair. It's going to be A3 and C4. Right? That's the problem we want to solve. And R is simply this guy over here. Right? I'm just not going to copy. By definition, it goes like this. It's going to be, number 1, the T, which will be the second operand over here, which would be A3, C4. And just to remind you, this guy over here is really the T. The T here. Union with some domain subtraction. Union, some domain subtraction. It will be R, domain subtracted, the domain of T. What's the domain of T? A and C. Agree? That's the domain. So I'm going to put A and C. And you can put a bracket around just to be emphasizing. And this will be basically the R domain subtracted by the domain of T. And notice that one thing here, if I take out the domain, can you say R domain subtracted T? No, you cannot. The type is not compatible, right? Whenever you do domain subtraction, it's going to be a set of the first values in the pair, not really like a relation, right? So type is very important here. And what's this then? What is R domain subtracted AC? Well, that means you're going to get rid of A here, C here, A here, C here. And what's really left? You got this left, this left, this, and this. All right? So this one here is really B2, and then B5, and then D1, and then E2, and then F3. All right? And then if you union them together, it's going to be, I'll put a space over here, put a here. You can definitely put them together. Basically, this set and this set union together, there's no overlap. So put them out. Right? You can put everything here. You can do that. Right? You can also see the slides. So what I have just done here is just by applying the definition and with a little bit algebraic rewriting to show to you how to calculate the relational overriding. However, I'd like to give you a little bit more intuition about what the operator is really saying. But we'll do that in just one moment. I'll pause a bit to make sure everybody is comfortable with the computation we're doing here. I'll say overriding is actually one of the more commonly used operators that we're going to need. So it's important to get the intuition right. All right, let me create a new page and give you guys a little bit more intuition. Oops, didn't copy the relation, right? Sorry about that. There we go. All right, let's now revisit this example here. Okay. The way I see this more intuitively, of course, it would be consistent with the formal definition, but this might be a little bit easier for you to think about. So when I say art overridden with this, it's basically R. All right, that's the first point. This kind of corresponds to what we said here. This will be a little bit here, except all pairs with the first elements in the domain of T. This is T, of course. Should agree. So in some way, think about T over here is more like changes that we want to apply to some big relation. The big relation that we apply to, in this case R, is going to remain basically the same, except the parts that we want to change, they have to be applied into the relation. Okay? So how do we see that? Now, given this relation here, we want to choose all the pairs where their first element is going to be in the domain of this one here, so A and C. Choose them all first. A here and C here. Let's get this one here, this one here, this one here, this one here. Right? So these are the AC involved pairs. All of those should really agree with T. If they don't agree, they should not belong to R. They should be taken out. Right? They should agree. All of them should be there. So it will be as if, in this case, get rid of them. And then simply put back T. A3, and then C4. So the resulting pair will be 1, 2, 3, 4, 5, 6, 7. So that's going to correspond to what we calculated in the previous example, right? It's basically doing the same thing, but now you're thinking a little bit more intuitive in the sense that we basically want to apply changes to the relation R. And these are domain values we would like to change their corresponding mapping value, 3 and 4. So we want to make sure those are there. Anything that doesn't agree with this should go out from the new resulting relation, overriding. Okay, that's another way to see it. See which way you prefer. If you prefer just applying the formal definition here, you can feel free. That's not a problem. But if you want to use this intuitive definition, that's also fine. You can easily show that it's consistent with the formal definition. All right, any question about overriding? But once we get the transfer events for lab number 1, we can reaffirm this intuition. Okay? I'll put some notes over here. How about that? And you can, as you are reviewing your lab number 1 solution for the transfer, you can think about it as well. Okay? I'll put it right away. So you may want to think about the transfer event from lab number 1. All right? So now you want to consider the changes over here that we want to apply. What's really the changes for transfer? Remember in that lab number 1, we say if every account should really match to their balance, right? That's A1 and A2. We want to transfer some money from A1 to A2, right? So changes over here would be something like, now A1 should really map to their balance minus certain amount. And also A2, they should be mapped to their old balance plus the amount. right? That one should seem familiar to you, right? That's the two pairs we want to somehow do the transfer. But why are we doing overriding? Think about these are the only two accounts that should be changed. And for A1, this will be the new balance. For A2, this will be the new balance. And now, when we say the original relation, in this case, it will be just the B, the bank. The B. Right? That one will be simply the account relation, let's say the integer, right? Something like that. And we are saying that we're going to basically keep the same bank relation like this. But the only two things we're going to make sure they agree after the overriding is these two accounts. Okay, that's another connection you can make to understand overriding. All right, any question about this? All right, so that's about overriding. And then I think that before we move on to the next operator, I think we should do a little bit more algebraic properties, which I got on my notes over here. Okay, let's do, all right. You can also see this one in the slides, right? So this one here, for this one here, we already seen the relational, sorry, not this one here. This one here, we already have done that. That's the easy one. Sorry, that's the harder one, which we already solved. As we said before, the relational overriding, if I got, let's say, R overridden, I got to remind myself here. T will just be T union with the R relational subtraction the domain of T, right? That's something we just did. So that'll be the answer to this question here. And if you want to see a solution derivation, you can go back to the previous part. And let's see another one here. How about this one here? We talk about image, right? If I want to find out the image of some set S on R, relation R, so this, something like this. Relation, and then S, right? That's something we talked about last time. How do we define this in terms of other relational operators? How do we do that? So some hints for you. You may need some kind of restriction operator, okay? How about I start you with a little bit? I know this is kind of hard, but you guys can think about it. If I give you something similar, of course, you got to take some time, to think about. I'll start you with. Can I say R relational image on S? Can I say that one is simply equal to, let's say R, domain restricted to S? Can I say that? This is my kind of a reasoning. I know that my R is something like this. And I'm somehow restricting to, let's say S is simply equal to, let's make it up. Let's say AB, for example, right? If I say I want to get a relation of R on this AB, this set, I'm saying that why don't I do a restriction of R into all the S element here, which will include this one here, A, B, that's it. 1, 2, 3, 4. That's kind of the idea. But that one is almost giving me the correct answer. But is it really giving me the right answer, though? Am I missing any step here? Anybody? Sorry? So is this, okay, so think about this. When we talk about relational image, right, is that a single set of elements or that's more like a relation? Right? You guys may want to review, right? Make sure you understand that you might need to use that for your programming test, right? This is basically a subset of the range of R. That's something you can check the definition, all right? That's a relational image. But now, is this expression over here going to give me something related to this? That's the question. Anybody? Yes or no? Yes, that's nice. Okay, very good. If you don't really see that, okay, that's important to know why it is wrong. So this alone gives you a relation. And a relation is going to be a set of order pair. Something like this. That cannot be a subset of the range of R, right? The range of R is simply a single element, like a 1, 2, 3, 4, etc. So it's not going to be good. And as you suggested, so maybe the way to do it would be to say the range of that. All right, so that will be the correct answer. So what you really want to think through when you go back home is to think, okay, now I know the relation image of R on S should be a subset of range of R. I know that. And this kind of idea about image is I want to get all the pairs that somehow related to S, the first value. So it's really like a restriction idea. But if I only put this one alone, the types are not really compatible. So that's why I need to apply further just on the range. So now the range of something is going to be a subset of this range, right? So that's how we check the compatibility of the types, right? Yeah, I think going through some algebraic property really help us understand a little bit more about how things should work together. It is very important. All right. Why don't we do 2 more easy ones? Right? Let's say this. I'll write them out, and then you tell me if you're convinced. Let's say we got some relation R, and then that will be a relation between S and T, right? It's a relation, single relation. And then, so we got little s, a subset of capital S. We got little t, capital T. Right? You can see here, S here, also T here, T here. All right? And I'm going to give you 2 properties. How do I somehow reconstruct R using subtraction or restriction operator? Right? That's the question. Okay? I'll write down the question here. You can think about it when you go home. So the problem is we want to reconstruct relation R in terms of restriction and subtraction. All right, that's the problem. Okay, I'll give you one rule to think about to start with. Let's say if I got one set already, right? That's a set. If I say R is going to be, let's say, R domain restricted to S. All right? Union with R domain subtracted by S. Does this hold? Right? I'll put a question mark over here. You can try to verify that. I got another one for you. You can also try to see. Okay? R would be, let's say, R range restricted to T union with R range subtracted by T. Right? Also, I put a question mark over here. And I'm going to put some example for you to try, right? Give it a try. And we don't need to do that in the class, right? So some examples here. You can use them to verify. For example, you can say R is simply equal to A1 and B2 and C3. And then we got little s, right? It's going to be, let's say, BD. And the t over here, let's say 1, 4. Oh, by the way, there's something I should really mention. So the S over here is really a bigger set. It will be A, B, C, D. Otherwise, you might be wondering. And the T over here is really 1, 2, 3, 4. So your exercises consist of 2 parts. I would say for the first part, try to check to see whether this equality really holds on this particular example, number 1. Number 2, does this hold in general? That's something I would like you to think. No? Okay, that's the video exercise for you. If you want me to verify your answer or check some understanding, reach out. Okay? Like that. Okay. Okay. Any other questions before we speak maybe briefly about lab number 2? I think I would like to help you with some axioms over there. I think we have covered enough operators for the beginning for the part 1 of lab 2. So we can now talk about it. Okay. Let's now take a look. So we'll talk about lab number 2 first, and then we can take a short break. Okay? Right, well, that's your lab number 2. I presume you have started and also read about the problem, but we can consider it again. So lab 2 really exemplify the format you're going to see for the programming test number 1 and 2. So given the informal English description, which will be here, we're going to read it together. You actually have to formulate from English to over here somehow. Right? That's something we will have to see. But we're going to see one by one. And also, we got some example there on the instruction. I can reuse that example to show to you how you can understand it. Let's see quickly. So we got persons. That's a set we're considering, like a carrier set, right? Oh, like a carrier set. It's all the person, set of person. And then we got celebrity. So we talk about celebrity C. It's a special person, but it's still a person. So C is a member of P. So that's exactly what you see over here, right? I'm just trying to show you the correspondence. And then, so here, this is to say, when you say the set of person is simply N, we are saying that all the persons are unique, and we can say they are simply a subset of natural number. Can be 0, 1, 2, 3, 4. Think about those unique are the IDs for each person. So we are model the set of person via unique integer IDs, starting from 0, of course. So maybe a person can be 0, a person can be 1, a person can be 10. But all the persons have a unique ID. That's what we got so far. And we have a relation, right? The nose relation. Now, if you take a look at that, let's not worry about this one just yet, right? This one may cause some confusion because we see some restriction over here. But why don't we say this? Like an intermediate version. When I say K over here is a relation, so it's a member of the set of all possible relations between persons. Let's start with this. Okay? And we know very well from our lecture already, this one basically will be equivalent to when we say K is a member of the power set of the cross product between P and P. Right? And one example, as you can see from the instruction over there, example. So we say, for example, let's say P will just be Alan, Mark, and Tom. Mark and Tom. And of course, what will be the maximum relation we can go between P and P? The maximum relation will just be the cross product, right? In which case, since we got cardinality of 3, so what will be the size of the maximum relation? 9, exactly, 3 times 3, right? That's also something we talk about in class. We're just verifying it. And if you, the relation I gave to you in the instruction, let's copy that down, and then we'll see what's special about it. And we say K over here is the nose relation Let's say this one here. Let's say Alan Mark. Also, we got Alan Tom. Also, we got Mark and Tom. This is definitely a relation. Because you can see the domain, Alan and Mark, definitely a subset of P. Also, Mark and Tom, the range is definitely a subset of the P. Right? So that's good. Right? It's also another way to see that it's a subset of the cross product. This is also a subset of the cross product between P and P. Right? That's also another observation to make. All right? The nose relation. How do we interpret that? Did you guys take that prologue course? Maybe the AI course? Don't know if you guys need to take. Okay, never mind. Maybe that was for CS. Forget about it. So how do we interpret this nose relation? We say the order does matter. We say Alan knows Mark. Alan knows Tom. Mark knows Tom. On the other hand, you will see the k to the power of -1. What is that? Inverse, right? How do we interpret that though? Let's now do that right away. If I got k, I can put tilde over here, or to the power of -1. What about that? Easy, I can put it down. It'd be Mark Allen. Right, just switch the order. Mark Allen, and also Tom Allen. And finally, I got Tom and Mark. All right, how do we interpret that? In this particular case, it's not too bad. So let's compare the pair one by one. This guy here and this guy here, right? One belongs to K, the other one belongs to K inverse. So here we say Alan knows Mark. So here, this will be Mark is known by Alan. And also Tom is known by Alan. And also Tom is known by Mark. That's how you interpret that, right? You want to see from these concrete examples before we can consider things like this. Okay? Are we good so far? Okay. And let's now try to see how we can translate each of the requirements over here one by one. So we got requirements number 1 here, number 2 here, and number 3 here. Let's see one by one. The first one. No person knows themselves. Okay? The way the instruction put is one way to express that. I'll show you some alternative. This is to say, whatever K, the nose relation, for example, this one here, you put, it must be the case that their intersection with the IT relation, the ID relation, identity. And you can look at the formal definition for identity relation on the instruction. I'm not going to copy that down. Look at that. Now, what will be the ID relation for our P over here? That's something you would like to see, right? So the ID relation in our case could be something like this. It would be Alan knows himself. Also, Mark knows himself. Also, Tom knows himself. So think about this ID relation here is something that's forbidden by requirement number 1. We want to make sure it doesn't happen. So this invariant is saying whatever knows relation K, you want to make sure it does not contain any pair that's in the ID relation. So to make sure nobody knows themselves, right? So that's why it should be, intersection should be empty. Any question about this one here? Right, that's one way to specify using just some set operators. Yes, question? No, because celebrity is a person, so they don't know themselves. So ID here, you can see I put Alan, Mark, and Tom. Tom is a celebrity, so Tom does not know himself either, right? Yep, also you can see from the requirement, no person knows himself or themselves, and including celebrity, also doesn't know themselves. Yeah? Okay. All right, so now for invariant axiom number 5, there is an alternative way to write it. Let's see. We can use maybe some predicate operator. Okay? Let me now put it here. We can say for all. How do we say that? Somehow we want to say for every possible pair in the relation, we should never get a pair such that a person knows themselves, right? Do you see what I mean? Let me start you with. For every, let's say P1 and P2, P1, P2, let's say, in the knows relation implies what? I want to make sure P1 and P2, if there are two persons, what should be forbidden? They shouldn't be equal, not equal to, right? So this will be P1 not equal to P2. That's another way to put it. You might find this more intuitive, right? But you should know both. Right? This will be some alternative to axiom number 5. And in the actual programming test, if I said you have to use set operators, you may have to follow this style. If I said you have to use a predicate logic style, then you might want to go for quantifiers. And in which case, you have to know how to do universal quantification for existential in rodent. Right? So this one here or this one here, they both work. Okay? Let's now take a look at the next one. The celebrity knows no one. All right? If the celebrity knows no one, well, how do we model that, right? According to your instruction over here, axiom number 3 over here actually models requirements number 2, right? According to your instruction. Now, how do we see like these two are related? Okay? Basically, you're saying this. The knows relation goes like this. The first element over here is always about Alan knows Mark, Alan knows Tom, Mark knows Tom. We never say anything like a Tom knows somebody because of these requirements, because the celebrity knows no one. Or put it another way, the celebrity himself or herself should not appear in the domain. Make sense? Okay, so now let me write something that might be slightly more intermediate using predicate logic. Or just put it another way. Over here, you might just want to say, sorry, not predicate logic. You may just want to say some intermediate property to say the celebrity should not in the domain of the K. Sorry, not K. Beg your pardon. Domain of K. That's what I meant. Agree? I can tell you what the difference is between these two. Okay? If you look at this one here, it's definitely easy to understand. I'm just saying that celebrity does not exist in the domain, meaning that Tom, in this case, does not know anybody. That definitely maps to number 2. However, in this case, what we are doing here is to declare the type of K. In that case, we have to say what type of function it is. That's why you have to use a membership and say this. Simply by saying it is not something, it's not enough for the rodent to know. You got to say what it is over here, right? So this is more like a typing constraint, but we'll try to understand it. Once you understand the intermediate one, it's easier to understand this ultimate one. So this more is like a typing constraint. Yeah, sorry for overlapping the fonts a little bit, but that's typing constraint. Now you can see much better, right? Now we're basically saying the nodes relation is basically a relation between P and P, except now the source set over here, like a S, cannot contain C. You got to make sure you don't ever put C inside the domain, right? That's how we do it. That's set difference operator. Okay, this is to say whatever relation you're going to, whatever relation K is, you got to make sure its domain cannot contain C because there's no C to choose from the S, right? That's how you understand it. So if the test asks you to really declare this relation over here for K, you cannot just say that. That's just a property to observe. But it might be helpful for you to understand. So if you want to declare the typing constraint, you got to say something like this. Okay? Let me say one more thing. When I say the nodes relation, okay, is P set difference C relation P, right? That's what you have for axiom number 3. This single typing constraint is equivalent to two things together. K is a relation between P and P. That one is very easy to understand, no restriction here. At the same time, K celebrity C is not in the domain of K. These two are equivalent to that single one. These two simply equivalent to this one here. They're the same. So in the test, if I want you to do a single line, you want to do the green one. If I don't have that restriction, you can feel free to go for the pink one to say it's a relation, but now I want to make sure the celebrity does not know anybody, so it's not in the domain. Okay? Either to use this one or this one, you should judge, depending on the instruction given to you. Okay with this? Okay? Hopefully that's better. Yeah, once you understand how to manipulate these operators better, I think task number 2 will be easier. Of course, please attend the scheduled lab session tomorrow if you need help. And the TAs will be there to help you. All right, the final one, which might be the trickiest one, because that one is going to use some inverse, right? But it's not too bad, I can tell you. Let's say this one here. Let me use blue. Everyone knows the celebrity. Well, put it this way. Celebrity is known by everybody. Agree? Celebrity is known by everyone. However, when I say this one here, you gotta be careful. Because of the restriction we got for number 1, celebrity should not be known by itself. Agree? Okay, so you gotta say, celebrity is known by everyone except themselves. That is to say, because we know Tom in this case is the celebrity. According to number 3, we want to make sure Tom is known by Alan. Tom is known by Mark. But we shouldn't have anything like a Tom is known by himself, which we don't have. So that means K is valid. All right? Let me say it again. Requirement number 3 here to say no, everyone knows the celebrity. Another way to put it is the celebrity is known by everybody, and by putting together with requirement number 1, you want to say celebrity known by everybody except it's not known by themselves. So that's why you will see something like this. When you see K to the power of -1, it's really like this relation over here, right? Tom is known by Alan, and Tom is known by Mark, right? That's really what we have. And now if you put the celebrity there, celebrity C, and now you can see Tom is known by Alan, Tom is known by Mark. Once you get a relational image of the Tom, what do we get? We get Alan and Mark. That's exactly all the persons over here except for the celebrity. Let me do it again. Let's now be very clear about how to understand this axiom number 5, axiom number 3. Okay, let's now do one more illustration, and then we should be ready to move on. Axiom number 4. Right, let me illustrate to you how that one should be understood. Okay, let's make it complete. Axiom number 4. K inverse relational image, and then the celebrity over here, and then equals P. Okay, over here, this part over here tells you celebrity is known by. That's how you interpret that, right? That's the inverse relation. And we talk about celebrity only. This means everybody except himself. Every person except the celebrity themselves. And let's apply this to the example, and then that'll be it. All right, let's now take a look at the example. Let me just copy this one here. Yeah, bear with me. After this, we can take a short break. Okay, I don't need this. I can get rid of it. So that'll be the K inverse over here, right? So now think about the celebrity we have is C, right? In this case, we got Tom. In our example, it's simply just Tom. So once you construct the K to the power of -1, which is this particular relation here, now if you get a relational image of Tom, which is the celebrity, right? You will get Alan and Mark. That's what you will get, right? That's a relational image. So K over here, Tom, is exactly equal to Alan and Mark. Now, finally, how do we interpret this? This one is to say celebrity Tom is known by, right, the inverse. Everybody except Tom. And when I say everyone, because we assume the P here is simply Alan, Mark, and Tom, right? Yeah, think about this process over here. I know it might be a little bit confusing in the beginning. That's absolutely normal. This might be the very first time or second time that you're actually trying to translate formally from some informal description into mathematical description. So there are many details here. But one thing we should really appreciate, with such a brief expression over here in English, there should be no ambiguous interpretation. It's a matter of if you really understand what's going on. Right? There should be no ambiguity here. All right, recap. So before maybe tomorrow, the scheduled lab session, if you intend to come for further assistance for task number 2, I would suggest revisit the problem description over here for requirement 1, 2, and 3. And then try to really see the correspondence into these axiom number 3, 4, and 5. Convince yourself you can create different examples, maybe a bigger set if you wish, and then really go through what we described today. Right? You might get something similar, maybe in the test, or maybe later. Question? Sorry, say that again? Oh, you don't need to. For the ID function there, it's predefined for you. So whenever you got ID here, you can just use it. And the definition for ID is what I put on the on the instruction. It's basically from every element mapping to itself. In our particular context, Roden would know you're really talking about the ID is really Alan, Mark, and Tom. Okay, you don't need to define that site. You don't need to. Axiom 3, yes?
So, can you explain why is there the arrow which relates like why is it?
You mean, okay, first of all, it's a relation over here because we got a set of pairs, right? Because knows relation is about somebody knows somebody else. So it's a relation over here. And then we are saying that everybody can be known by somebody else. That's okay. So there's no restriction on the range. However, the person who knows about somebody else, we got to be careful because celebrity knows nobody. Yeah, that's why we get rid of it. Okay? All right, guys, any more questions before we take a very short break? Tricky, but I hope that will help. You know, take some time to think about it. You still got a week to get used to it. Okay, why don't we take a very short break for 2 minutes and no attendance today. All right, so now let's go back. Let's see where we are in the slides. So today we basically talk about overriding thoroughly. And the 2 exercises, we definitely did it. And then we went on to talk about lab number 2, right? Which we talked about also before the break. And let's now move on with the math review. So the remaining part for the math review, there are several items over here. So today, I think for the remaining 14 minutes or so, I'll go over what a function is and get some conceptual idea about what function should be related to relation. Let's do that one first. And then when we come back on Thursday, we can talk about the different properties for function. And also there are 3 kinds of function we need to worry about: injective, surjective, and bijective. Right? And finally, the most important item, which I'm going to use to conclude the whole math review, is to consider some modeling decision to see whether we should use a relation, should we use a function for our type. That's something we'll see. But one thing at a time. All right, let's now talk about functional property, right? And number one thing for you to know, a function is really just a relation, first of all. It's a relation. It's a special kind of relation. And this will be the property to satisfy. I'm pretty sure you have seen that maybe back in 1090, but let's review that to get more insight. Okay, why don't we do that? Okay. Number 1, we want to know, so R over here is a relation. So R is a member of S relation T. R is a relation to start with. And we're saying that there's certain R that is at the same time, it's a relation, but at the same time it's also a function. So the conceptual view goes like this. Think about this will be the larger, much larger set for all the relation conceptually. And there will be a much smaller set of relation that are also qualified as the function. I think this diagram here is very important because once we have gone through the lecture on Thursday, we're going to have many more circles in this diagram. So now it's good to get this one done first. All right? On Thursday, we're going to define partial function, total function, injective, surjective, bijective. And how do we draw them here? But that's for Thursday. For now, make it simple. And one thing you should know right away, which we kind of briefly hinted when we talk about subset, right? So the set of functions over here should be a subset of relation. Proper subset to be more precise, because there would be some relation which is simply not qualified to be a function. Some function not qualified. To be a relation. Yeah, we'll talk a little bit more about this when we see a detailed example on Thursday. But with the 10 minutes, let's see what we can do. So given some relation, what does it really mean? R is also a function, which will be here, right? As you can see, if I got something over here, if I got, let's say, a dot over here, that means it is a relation and a function at the same time. A relation and a function at the same time. That's okay. Question? Not qualified to be a function. Yes, 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 yes. What am I doing here? Thank you so much. I said exactly the opposite, right? That's not really what I was thinking, but I blame myself for that. Thank you. Some relation, that's not a function. Not qualified to be a function, absolutely. Yeah, I said exactly the opposite. Sorry about that. Okay. All right, so make sure you understand this diagram, very easy. And now let's see, what does it take for a relation to be qualified to be a function? Okay, we'll do one small example, very small one. Okay, let me put it right away. Let's consider this particular example. Let's say we have a relation here. Let's say A1 and also B2 and also A3. Would you guys agree this is a function, this is a relation because we got set of order pairs. Easy to see, right? Set of order pairs. A1, B2, and A3. But now, does this satisfy the functional property? I can tell you it does not. But let's see. Let's use this example here to understand the functional property a little bit better. Okay? Now, this one is saying that it would be a function if for every S, like A, B, or A or B, for example, over here, and then for every range value, T1, T2, and now you say that, think it this way. S over here is a domain value. And these two are the range value. Right? Basically, we're saying that. And then you're saying that if these two pairs are in the function, let me annotate this one here a little bit more carefully. This one is saying these two pairs sharing the same domain value is in the same relation. Two pairs sharing the same first value. In this case, of course, they are sharing the first value here, right? But T1 and T2. It would be a function if T1 and T2 are exactly the same. Okay, and we'll see what the consequence it really means. Let me write it down. So here we say the second values are the same. The second values are the same. And this really means ST1 and ST2 refer to the same pair. You can think about it, and we're going to have some rewriting in just a moment, right? This one, they should really refer to the same pair. Let's see why this particular one is going to violate the functional property. Let's see that first. Can you find S, T1, and T2 such that this pair is in R, and this is also in R, but this is not the case? Can you find such as T1 and T2 in over here? Anybody? For example, this could be S. This could be S. Right? And then you can also see that the one here could be T1. And the 3 here could be T2. All right? That's simply just some combination there. And now you can see that ST1, A1 is in this relation. And ST2, which is A3, is in this relation. Now, is 1 and 3 over here the same value? They are not the same. So what does that mean? That means the same domain value is mapped to distinct values in the range. That's not a function. So the most important functional property you want to understand is, for the same domain value, they can now map to distinct values in the range. That's really the key. All right? So overall, this is what you want to remember. The same domain value cannot map to distinct values in the range. This is so important to note. All right? So what we have said so far is you want to really read through this formal definition for functional property. In order for the functional property to be violated, one way to do it is you want to choose the ST1 and T2, like what I did, ST1 and T2. And these two pairs, apparently they are in the relation. And they share the same first value, which is A. However, the second value over here are distinct, meaning that the same domain value is mapping to distinct range value. That's not a function. It's only a relation. All right, that's something I have just said. All right, let's now try to answer some question over here underneath. Let's try. Yes?
Let's say it's not a function if you have the same S to two different distinct.
Mm-hmm.
But would it be the case that it's a universal, like let's say distinct S to same?
Yeah, okay, very good. So your classmate question definitely makes sense. It goes like this. If you have the same domain value that maps to distinct range value, for sure, it's not a function, okay? You were asking something like this. What about distinct domain values map to the same range value, okay? I can look ahead to say. So now let's say a relation over here. Let's say A1 and let's say, and also B2, and also C1. All right, this is a different case. You basically got, let's say, A here, C here, and we map to the same range value, okay? This one here, you can definitely check. That's something I can do maybe quickly next time. Check this against the functional property. And you should really get the conclusion that it is satisfying. And the second one I want to look at is this is something called an injective function. So it is a function where you actually got two distinct domains, value mapped to the range. It's a function. It's called injective, which we'll see the definition next time on Thursday, right? But what you should really try is to take this relation over here and check against this formal definition here. It actually is satisfied. It does not violate, all right? We got 2 minutes. Why don't we answer a few questions, and then we're done, okay? Question number 1. Based on this definition over here, what would be the smallest relation that can satisfy the functional property? Smallest one. To be honest, every time I say smallest one, right, it's almost always true when you say empty relation, right? Let's see why. Because in the functional property over here, we actually got an implication over here, right? Or you can think about this implication here. Are you able to find any ST1 and T2 in the empty relation? Not really. So the antecedent is already false. False implies anything, right? You cannot find anything, right? That's why it's the smallest. But in the actual test or exam, I might ask you to explain. why empty set is the smallest function. Make sure you know how to do that, all right? Which I just explained. I will do number 2 next time. It will take a little bit more time, how to prove or disprove. But basically, it boils down into the implication that we have over here. You can think about it. I will just talk about contrapositive, which I can also do next time. But let me just remind you, contrapositive, P implies Q should be equivalent to not Q implies not P. That would be just another way to interpret the functional property, which we'll do on Thursday. All right, so on Thursday, I really want to try to finish everything about a review. Next Tuesday, we'll start building the bridge controller. All right, thank you. I'll see you maybe in the schedule lab tomorrow.